Hey guys, let's talk about titrations. Titration is a lab method. Typically, it's most used for acid-base reactions because we can use an indicator to tell us when to stop the reaction with acids and bases. However, it could be for any type of reaction, especially redox reactions where you have different oxidation states changing colors, and so that's when when the color changes, that's when you know that the reaction has reached equilibrium. But for the majority of the time, we use it for acids and bases. So the way that it works is one of your substances that you're reacting, you put it in a burette, and in acid-base reactions, typically, it doesn't have to be like that all the time, but most of the time, we put the base in the burette, B and B. And then we have an Erlenmeyer flask where we put the other substance. And again, most of the time, since we put the base in the burette, then we put the acid in the Erlenmeyer flask. And along with the acid, we typically put the indicator in there. And we know how much acid we've added. We usually fill the burette, record the initial amount of base in the burette, and we keep adding the base drop by drop and swirling until the color of the indicator changes. Then we stop and we read the final volume of the burette so that we know the volume of acid that we have, the volume of base that we have. Typically, we know the molarity of one of them, and usually what we're looking for is the molarity of the other. The substance that we don't know the molarity of or that we want some information about is usually called the analyte because we're analyzing it. The other substance is called the titrant because we're titrating the unknown with it. And so, again, titrations are a method in the lab to determine usually the acid or base strength or concentration using a known standard. And the standard is typically a solid, an acid or a base solid. Like, for example, if we're standardizing sodium hydroxide, meaning we're trying to find the concentration of it, we use potassium hydrogen phthalate, which is a weak acid that's a solid at room temperature. So most of the time, that's a solid standard here. Titrations can be monitored by a titration curve. So you could put a pH probe in there and keep measuring the pH and drawing a titration curve to know when you're done, or you could use an indicator that changes colors. So last year we've used indicators. This year we're actually going to do titrations with pH probes, so you would not need an indicator in that case. When you do a titration, let's say you are recording your pH. So you can draw something called a titration curve where there's your pH and this is your volume of base that you're adding if you're doing it the way that we have it drawn there with the base in the burette, so you're adding it slowly. So initially in your flask you have just the acid, so it starts at a low pH, and then your pH starts increasing, kind of increases slowly, and then it shoots up, and then it goes slowly again. We call that an S curve, typically, because it kind of looks like an S. If you were doing it the other way around, where let's say that your acid was in your burette and your base was in your flask, so now we're adding the acid to, we're adding the acid to your Erlenmeyer flask. So initially, your Erlenmeyer flask would have a base, so it would start at a high pH, and then it decreases kind of slow, shoots down, and then it goes down. So it almost looks like a Z. It's the opposite of the S curve there. So where you have the steep slope here, whether it's here or in the other one, where you have two inflections there, you find the two inflection points, and then halfway through the inflection, so right here, and then right here, that's what we call our equivalence point. So this is your equivalence point. The equivalence point is when exactly enough titrant has reacted with the anil. It's using the stoichiometric ratios. So if they're all 1-to-1 ratio, when 1 mole of the acid has reacted with 1 mole of the base. Or if it's a 2-to-1 ratio, then when 2 moles of the acid has reacted with 1 mole of the base. So when you've reached the correct stoichiometric ratio, so there's no excess reactant, no limiting reactant, they all have reacted exactly completely to use up each other, that is when we say we've reached our equivalence point. If it's a 1-to-1 ratio, which we'll see in this year, we're not going to do any stoichiometric ratios that are not 1-to-1. In this case, the moles of the acid are going to equal to the moles of the base that I'm using. Now the end point, typically we try to have the end point where the equivalence point is, but that's not exactly when it happens. So the end point is when the indicator changes colors. So what we do is we look at the type of titration we have, and we kind of have an idea of when the equivalence point would be, like what pH it would be. And so we pick an indicator that will change colors at that pH. For example, let's say I'm titrating some acetic acid with sodium hydroxide, and I know that the equivalence point will happen when the pH is around 8 or 9 or so. Then phenolphthalein would be a really good indicator because phenolphthalein turns at pH 9. If I'm doing another reaction where the equivalence point is at pH 5, let's say, then methyl red would be a really good indicator for that because it changes colors around pH of 5. So you want to pick an indicator that changes colors around your equivalence point so that, that's when you see the color, you stop your reaction. However, because the equivalence point happens in the middle of this really steep sloped line here, it's almost vertical, right? And so if you pick an indicator that turns at a pH anywhere close to it, then that's okay. So if this was my equivalence point, for example, if I pick an indicator that will change at this pH or even at this pH, anywhere in this range, this is vertical. When I read the volume of the base here, it is pretty much the same, right? And so if I pick an indicator that will turn anywhere in this range, I will still be okay. Same thing with this one. If I pick a pH here, an indicator that will turn anywhere in this range of pHs, I will still be okay because it's still the same volume of base that I'm adding, that, because what happens is the pH changes very, very, very slowly, and then it shoots up. So one drop of base would make it, let's say, go from pH of 5 to pH of 9, for example. And so if I pick an indicator that will turn anywhere in that range, I would still be okay because I would know when to stop it, and that would not change my volume of base. So again, the end point is slightly different from what the equivalence point is, but you usually want to pick an indicator that will have an end point where or close to where the equivalence point will be. There are several types of acid-base titrations. There are 4 types, but we're going to focus mainly on 3 of those types. So the first type is when you have a strong titration, meaning that you have a strong acid and a strong base reacting together. If you have a strong acid and a strong base reacting together, your equivalence point will happen to be at pH of 7. That's not true for other titrations, only for strong. Now, the reason for that is, let's say you have some HCl, that's a strong acid, H plus and Cl minus, and a strong base like NaOH, so Na plus and OH minus. You combine these, you form water, molecular water, and then Na plus and Cl minus are your ions that are left over to make salt, so it's salt water. Well, water is one of your products. It has a pH of 7. And then your other two ions, Na plus and Cl minus, those ions cannot undergo hydrolysis because Na plus is the ion of NaOH, which is a strong base. Cl minus is the ion of HCl, which is a strong acid. And so those would never undergo hydrolysis, and so your pH would not change. They would just swim around in water doing nothing really. They're spectators. And so your pH will be a pH of 7. Again, that's for strong. Okay, let's look at if you have a weak acid with a strong base. So an example of a weak acid is HCN. This is molecular. Obviously, it's covalently bonded there. And then sodium hydroxide is our strong base, NaOH. So those react together. You form water, as always, which has a pH of 7. And then you form NaCN, which is your salt. Now, NaCN, it's in water, so it's going to dissociate into Na plus and Cn minus. It's really already dissociated. It's, the ions are swimming around. Well, the Na plus is the ion of a strong base, NaOH, so that does not undergo hydrolysis. However, the Cn minus can undergo hydrolysis, and so it does. So Cn minus, when it reacts with water, it grabs an H plus from the water to form HCN and OH minus. And so in reality, my products are some water, Na pluses are swimming around, and then some Cn minus, some HCN, and some OH minus. And so I'm forming some hydroxide ions in addition to all my neutral stuff. And so my equivalence point will actually be at a basic pH. My pH at the equivalence point will be greater than 7. It will not be equal to 7. The reason is because one of my products is an ion that undergoes hydrolysis to form a basic solution. Now, it's a common misconception among students to say, when I have weak acid with a strong base, the pH is greater than 7 at the equivalence point because it's a strong base, so it's stronger than the acid, and so it's going to win and have a pH that's basic. That is not true. The reason why the pH is greater than 7 is because one of your products is an anion that will undergo hydrolysis to form hydroxide ions, and therefore a basic solution. Now let's look at another scenario. What if you have a strong acid with a weak base? Like, for example, a strong acid is like HCl, so H plus and Cl minus there, and a weak base like ammonium hydroxide, NH4 plus and OH minus. They all combine, you form water, and then NH4Cl. Cl minus is the anion of a strong acid, HCl, so that does not undergo hydrolysis. However, NH4 plus can. And so it undergoes hydrolysis. It donates an H plus to the water, and so it forms NH3 and H3O plus. And so I'm forming some hydronium ions, which is acidic. And so at the equivalence point, when all of these have reacted, I end up with some water, and then some of the ammonium and the Cl minuses, but also some ammonia and some H3O plus are left over, and so my pH is acidic and it's less than 7. Again, this is a common question on the AP exam. For a strong acid or a weak base, what would be the pH at the equivalence point? The answer is it's lower than 7. Another popular question is why? It's not because it's a strong acid, so it's stronger than the weak base, and so it's going to win and be acidic. That's not the reason. The reason is because one of your products is a cation that will undergo hydrolysis, giving off H pluses or hydroniums. And so your pH would be less than 7. Now, the fourth type of titration would be weak. So weak acid, no E there. weak acid with a weak base. What would the pH be? Well, it depends. It could be 7, it could be lower than 7, it could be higher than 7. What does it depend on? It depends on your products, because what will happen is the products of both of these reacting together, both of the ions would undergo hydrolysis. And so one of the ions will undergo hydrolysis to give off an acidic solution, the other one will undergo hydrolysis to give a basic solution. And so what you want to compare is the Ka and the Kb of those ions that will undergo hydrolysis, and that will tell you. Most of the time it will not be 7. Usually it will be higher than 7 or lower than 7, because very rarely will the Ka and the Kb match. One where they actually match by coincidence is if you have acetic acid with ammonia. So acetic acid with ammonia will actually give you a pH of 7. Those are both weak because the ammonium ion, the NH4 plus, and the acetate ion, the CH3COO minus, will both undergo hydrolysis. This one gives off H pluses, this one gives off OH minuses. It turns out that the Ka for ammonium and the Kb for acetate are exactly the same number, and so the pH will be 7. But that is just a coincidence. Most weak titrations will give you a pH of higher than 7 or lower than 7. We are going to look at doing calculations with all three of these, so strong, strong, weak, strong, and strong, weak. We will not be doing calculations with weak acids and bases. We will do a titration of these so you can see what the titration curve looks like. You would be responsible for that, but you will not be responsible for doing calculations except for these three, not the fourth one there. So that's why I don't have it listed. So let's start our calculations. We're going to start with strong acid and strong base titrations. Those would be the easiest in terms of calculations, because we don't have any ice charts or any hydrolysis or anything like that. It's just straightforward. So I have 50 milliliters of 10th molar HCl, and I'm going to calculate the pH as 10th molar NaOH solution is added. And so this is telling me that this is in my flask, my Erlenmeyer flask has my 10th molar, HCl. And then in my burette, I have my base and my burette there. All right, so let's start our calculations. And the first calculation I'm asked to do, I want to know what the pH is at each of these. And so the first one is for just the original acid. So if I were to stick my pH meter or pH probe into this flask before any NaOH has been added, how would I find the pH? Well, in here I only have some HCl right now, and HCl is a strong acid. And so my HCl dissociates into H plus and Cl minus 100%. If this is 10th molar, then this is 10th molar, and this is 10th molar. I already know what the H plus concentration is. pH is negative log of the H plus concentration. So negative log of 10th molar, which is 1. Or 1.0. All right, let's do the next one. The next one says, what if I add 20 milliliters of my NaOH? So right now, my flask has 50 milliliters of the 10th molar HCl, and I have 10 milliliters of my NaOH. Well, my NaOH and my HCl are going to react together, and so we're going to write our reaction between the two of them. Now, you have two choices. You can write HCl plus NaOH yields water and NaCl. You could do that, or you could just write H plus OH minus yields water, because we know that the Na plus and the Cl minus do not undergo hydrolysis, so, you know, those are just kind of spectator ions. Oh, I'm sorry, I shouldn't have erased that or crossed. There we go. So if you want to rewrite it as H plus OH minus yields water, that's acceptable as well. It's totally up to you. Anyway, what you want to do is write out your reaction, and then you want to write out how much you have, how much reacted, and then how much you end with. Again, this is not an ice chart as an equilibrium. This is a reaction that goes to completion. Usually when an acid and a base react together, the K is very, very high, that it's almost like it's going to completion, and so you know, we say it's an end as opposed to equilibrium. Meaning that's one arrow as opposed to equilibrium. So anyway, my acid, I have 0.05 liters, and it is 10th molar, and so that gives me 0.005 moles of H plus. So I'm going to write that down, 0.005 moles. Now, the reason I'm doing this in moles as opposed to molar is because I'm adding two solutions together, and my concentrations will change when I add them together because my volumes change. So I would say it's helpful when you're doing titrations to do these in moles as opposed to molarity, but then at the end change to molarity when you need the pH, of course. So my OH minus, I have 10 milliliters, so 0.01 liters, and it's also, I believe, 10th molar, yep, so 0.1 moles per liter, so that gives me 0.001 moles of hydroxide. So this is 0.001 moles. Don't really care about my water there. So out of these two, my limiting reactant would be the hydroxide, and so that's going to be used up. So minus 0.001 moles, and this is also minus 0.001 moles. And so at the end of my reaction between the two, I end up with 0.004 moles of my acid, and I don't have any hydroxide left. And so right now I have 0.004 moles of the H plus. If it's HCl, same thing as H plus, 1-to-1 ratio. My total volume, I've added 10 milliliters of NaOH and 50 milliliters of acid, so that's a total of 60 milliliters. So that's 0.06 liters. And so my concentration is 0.0667 molar of H plus. So my pH would be negative log of that, which ends up being 1.17. And so I started out as a pH of 1, and now after adding 10 milliliters, it increased slightly to 1.17. Let's look if I add 50 milliliters of NaOH, what would happen? Alright, so now in my flask, I have 50 milliliters of the HCl originally, and then I've added 50 milliliters of NaOH to it. So these two things are going to react together, and so let's write out our reaction. Again, if you want to write NaOH plus HCl yields water and NaCl, that's fine. If you want to write just H plus and OH minus forming water, that's okay as well, since it's strong and strong. We have already calculated our moles of acid. We have 50 moles of 10th molar. That was 0.005 moles. That's not going to change. My hydroxide, I also have 50 milliliters of 10th molar, and so that's also 0.005 moles. Don't care about the water. Let's look at which one is my limiting reactant. Oh, looks like they're both the same amount. so it doesn't really matter. And so that's going to be used up. Negative 0.005 will be my change. So minus 0.005 moles minus 0.005 moles, and I don't have anything at equilibrium. I just end up with some water. And my other product is NaCl, does not undergo hydrolysis, so it doesn't change my pH, and so my pH here would be pH of 7. We are at the equivalence point. At the equivalence point, my amount of acid has reacted completely with my base, and so I don't have any of my original acid or base. All the HCl and all the NaOH have been used up. That's your equivalence point. All right, and what if I keep adding base to this? So, normally if I had some indicator in my flask, it would probably have turned, one more drop would have turned it pink and I would have stopped there. But what if I keep adding NaOH? What would my pH probe read? Well, let's see if we can calculate it. So what if I add 10 more milliliters of NaOH? So let's say, just for fun, I keep adding some NaOH. What would be the highest pH that I could reach? If you look at my curve here, in this specific example, I don't have numbers here except for the 7 and the 14, but if it was this specific reaction that I'm doing with the 10th molar HCl and the 10th molar sodium hydroxide, that would start, we said, at a pH of 1, and it goes up very, very slowly as I add my NaOH, and then suddenly it just shoots up. This right here, this point is my equivalence point. That's when I've added 50 milliliters of my base, and that was at a pH of 7, just because it's a strong reaction. Shoots up, and then I keep adding base, and it goes up very, very slowly. So if I were doing this titration, I keep adding, if drop by drop, or even milliliter by milliliter, it would, at this point, after the 60 mils, let's say I added 61 mils, be maybe 11.97, then 11.98, and then 11.99. See how it's going very, very, very slowly. But at some point, that line will just be a straight line. It's not going to go up anymore. At some point, it's just going to remain steady. What pH would that be? Do we know? Is it 14? Is it 12? Is it 11? What does it depend on? Well, if you think about it, let's say I keep adding and adding and adding. Let's say I have the 50 mils of HCl and I've added like 100,000 gallons of NaOH. So it's really almost just all NaOH, very, very tiny amount of acid. What would the pH be? Well, the pH would be the pH of just my NaOH solution, right? Which is, in this case, 10th molar, so the pOH would be 1. So my pH would be 13. And so in this specific reaction, because I'm using 10th molar NaOH, that will always go slowly, and then stay steady. That will approach a pH of 13 in my specific case. What if it was 1 molar NaOH? Then that would approach, 14. If it was 0.01 molar NaOH, it would have approached 12, and so on. And so when you've added so much base that your solution is almost just base, it's going to be the pH of just the base. So a couple of things to know. If you were to sketch a titration curve, you would want to know what the original pH is. You would want to know what the pH would approach at the very end, which would be the pH of just the base. And then you also want to know what the pH would be at the equivalence point. If you know those three, then you can actually sketch a titration curve, which is kind of a common question on the AP exam.